So these examples, number 1 through 5 here, they were borrowed, I guess, or stolen, either way, from when I was a grad student. I actually took them from a Chem 1 test the professor that I was working with gave to the students. And 1 through 5 here really test your knowledge of the gas laws. There's short ways to do them and long ways to do them. And if you do them the long way, you will not have enough time. But if you understand the concepts and the principles, these are actually pretty quick problems. So let's dive in. 8-liter vessel. So that's an 8-liter vessel. That's a volume. Contains 5 moles of hydrogen, 3 moles of helium, and 2 moles of oxygen gas at a pressure of 25 atmospheres. What is the temperature of the gas, assuming the mixture is ideal? Well, this is a PV equals nRT. We're solving for T. So T would equal PV over nR. Yes, so T equals P. That's 25 atmospheres. V, 8.0 liters. N would be 5 plus 3, 8 plus 2, 10 moles. And R, of course, is R, 0.08206 liters, atmospheres, moles, Kelvin. So if we do this math for temperature, temperature is going to be 244 Kelvin. 244 Kelvin. 244. It gives me negative 29, just so we know, negative 29 degrees Celsius. That's number 1. Number 2. What is the partial pressure of oxygen gas in the mixture described in the previous question? So we're looking for oxygen. Partial pressure of oxygen, so we're looking for P of O2, and that'll equal the mole fraction of O2 times the total pressure. Well, we can do that. So my pressure of O2 equals, how many moles of O2 did we have up there? Well, if we look back up, I think we have 2 moles of oxygen gas over 10 moles total. And we had 10 moles total, correct? So there's our mole fraction, and the total pressure was 25 atmospheres. All right, 25 atmospheres is the total pressure. So P equals 2 times 25 would be 50 divided by 10, 5. So the pressure O2 would be 5.0 atmospheres. Perfect. Okay, number 3. Suppose an additional 7 moles of hydrogen is added to the mixture described previously without changing the temperature or the volume. What is the partial pressure of oxygen in the new mixture? Okay, so let's say this. PV equals nRT. What is changing? N is changing because we're adding 7 moles of hydrogen. So temperature is not changing. R is not changing. The volume is not changing. So if N changes, does P change? Well, it has to, right? So how do we attack this problem? Well, I guess we can use the ideal gas law, right? Because I know if N changes, the total pressure changes. Well, let's do that because it's no longer, because a lot of times here's what students in my seated classes will say. Well, pressure O2 now would be 2 moles over 17 moles times 25 atmospheres. And we'll get that number, which 2 times 25 would be 50 divided by 17. They'll say it's 2.9 atmospheres. And then I'll say, okay, good, but then we do what we just did here. PV equals nRT. If N changes, P changed, so 25 is not the case. So now we have to figure out the new pressure. And they go, oh, okay. So can we do that? Yes. So P equals nRT over V. So P would equal 17 moles now. R is still 0.08206 moles Kelvin. Temperature we know is 244 Kelvin. And it's still 8 liters. So my new pressure is 42.5 atmospheres. So now I come back here. Pressure of O2 is 2 moles of O2, 2.0, all over my 17 moles total, so my mole fraction, and the pressure is now 42.5 atmospheres. And if we do that, we get a pressure of 5.0 atmospheres. Wait a second. Did you get 5 in your calculator? Didn't we have 5 here for problem 2? So I added 7 moles of hydrogen and oxygen didn't change. Exactly. That makes sense? So if the problem read, suppose that Mr. Dupuy gained an additional 7 pounds over the holidays. How much do you weigh? Well, your weight didn't change if I gained 7 pounds, right? Or conversely, let's say I lost 7 pounds. What happened to your weight? Nothing. It's totally independent of my weight. So if we add 7 moles of hydrogen to the mixture, it does nothing to the oxygen. That makes sense? So this question could have been, 30 seconds. Just to realize we had hydrogen, oxygen didn't change, 5 atmospheres. But we proved it, which is wonderful. Now, number 4. Suppose that additional 4 moles of oxygen is now added to the mixture described previously without changing the temperature of the volume. Now we're adding oxygen for number 4. So since number 4 we're adding oxygen, what do? Well, we can go back to P equals nRT over V and get a new pressure. So if I add 4, I had 17, and now I have 4. Now I have 21 moles of total gas. R is still R at 0.08206 liters, atmospheres, moles, Kelvin. T is still 244 Kelvin. And the volume is still 8 liters. So the new pressure now is 52.6 atmospheres. So if we go back to my pressure of O2, mole fraction, now 2 and 4 is 6.0 moles, divided by the 21 moles, times by the 52.6. I didn't change color. 52.6 atmospheres. It looks like I should get 15. Which looks good. But we could have done this much faster if we realized that the pressure of O2 and the mole of O2. What happened here? The pressure went from 5 atmospheres to what? And the moles of O2 went from 2 to 6. So it's kind of like P over N equals P over N. If I'd have done 5 atmospheres over 2 moles, would equal X atmospheres over 6 moles. Right? And since that's a triple, that would be a triple. So 5 times 6 is 30, divided by 2, 15. So if we just know that the moles tripled, the pressure tripled. Right? Because V and T and R are constant. So this does really apply to if you have a good knowledge of the gas laws. This really does test how well you know them. That's why I like them so much. If you know the principles, you got it quickly. If you don't know the principles, you can actually solve it the long way and it works out, but it's just going to take you a lot longer to do. Number 5, last one of these 3, or these 5, last one. The mixture, after adding the 7 moles of hydrogen and 4 moles of oxygen, is now ignited to form water. So I have hydrogen and oxygen forms water. Hydrogen was a gas, oxygen was a gas. The mixture is cooled to the original temperature, and the volume does not change. The water completely condenses. It could also be a G. What's the total pressure of the gas at the end? Okay, so hydrogen. How many moles of hydrogen do we have? That's a good question. Well, we had 7 moles, and then to start with, we had 5 moles. So that would be, we had the 7 plus the 5, so that's 12 moles of hydrogen. Oxygen, we have 6 moles. We just calculated that. And what else do we have in here? We have, I think we have helium, don't we, in this mixture? Yes, we have 3.0 moles of He. But that's not going to react, right? It's a noble gas. It's inert. All right, find the limiting reactant. Who's limiting? Well, first let's balance. We need to put a 2 here and a 2 there to make this work. So 12 divided by 2 is 6. 6 divided by 1 is 6. Who's limiting? No one. They're both present in the correct ratio. And they're 100% consumed. And we all what's it going to make? It's going to make 12 moles of water, but we don't really care because water's gone. So that means at the end, we only have the 3.0 moles of helium. That's it. That's the only gas in the vessel or the container. Go back to the original. The pressure of helium, mole fraction of helium, times the total pressure. So the pressure of helium will be the mole fraction of helium, 3.0 moles over 10 moles times the 25 atmospheres, which is 7.5 atmospheres. Because helium doesn't change to all these 5 questions. So I like those 5 questions. Number 6. What is the density of argon gas at 1 atmosphere pressure and 25 degrees Celsius? So if you remember our density formula, density equals pressure times the molar mass divided by RT. So the density, the pressure would be 1 atmosphere. The molar mass of argon. Argon looks like it's 39.95 grams per mole. R, of course, is 0.08206 liters, atmospheres, moles, Kelvin. And the temperature is 25 degrees Celsius, which we have to add our 273 to get 298 Kelvin. So the density of this argon gas seems to be 1.63 units. Atmospheres are gone. Moles are gone. Kelvin's gone. Grams per liter. Fantastic. Number 7 is probably one of my sixth favorite problem. Why? Because it's actually a good thing. It's a good thing to do. We have unknown. Let's find the unknown. You have 5 gram sample of manganese metal, Mn, and we have 5.00 grams. This react with excess HCl. Yes, excess. So we don't know how much. To make H2 gas, and that has some stats. It's 8.36 liters, 373 Kelvin, and 1.00 atmospheres. And it makes a solid MnClX compound that we don't know. Right? What's the formula? So what is that X? And here's the thing. In real life, there's more than one option. Right? Manganese is a transition metal that can be several different oxidation states. So it could be MnCl2, MnCl4, MnCl3, probably 6, probably maybe even 7. I don't know if 7 exists or not. I have to look it up. But there's definitely more, and of course the problems, I could have 1 through 7 there, no problem, right? It doesn't actually have to, compound doesn't have to actually exist for me to ask you like a fictitious problem like this. So what do? Well, can I figure out how many moles of manganese? I sure can. If I take 5 grams and I divide that by manganese's molar mass of 54.94 grams per mole, I end up with 0.0910 moles of Mn that reacted. And that's my limiting reactant, so all that reacted. So I know over here we have 0.0910 moles of Mn. I need to figure out how many moles of Cl. But I have this H2 here. Can I use PV equals nRT to get the moles here? Can I do that? I think so. So N would equal the pressure of 1 atmosphere, the volume of 8.36 liters, divided by R, 0.08206 liters, atmospheres, moles, Kelvin, and the temperature of 373 K. So how many moles of H2 do we get? 0.27. 273 moles of H2 produced. Well, all the H2 came from HCl, right? So we have 0.273 moles of H2. I know that for every 1 mole of H2, there are 2 moles of HCl because it's a 2 to 1 there. And I know that 1 mole of HCl has 1 mole of H. So that means we actually produce 0.546 moles of Cl. So I got that. Well, if you remember empirical formulas, hopefully, I can just divide by the smallest here, because I'm already in a mole ratio, 0.0910, 0.0910. And I get 1 for manganese, which I expected, and it looks like I get 6 for chlorine. So my formula then is MnCl6. So what do? Recap. Found the moles of manganese, my limiting reactant. Figured out how much H2 I produced in moles. Converted that back to how many moles of HCl versus how many moles of Cl. Oh, I wrote H down. It should be Cl here, shouldn't it? How many moles of Cl, moles of manganese, and we just divided by the smallest, get whole number ratios. Mm, 62. Mixture with a total pressure of 745 millimeters contains each of these gases indicated their partial pressures. Okay, so my total pressure is going to equal the pressure of CO2 plus the pressure of argon, plus the pressure of oxygen gas, and the pressure of helium. So the first question says, what is the partial pressure of helium gas? And what's the mass of helium gas present? And it gives you a volume and a temperature. All right, so question 1, let's say. So we got 1 and we have 2. For 1, I'm looking for helium. So algebra, pressure total minus the pressure of CO2 minus the pressure of argon minus the pressure of oxygen gas will equal the pressure of helium. So the total pressure was 745 millimeters of mercury, minus CO2 was 125 millimeters of mercury. What's next? Argon is 214 millimeters of mercury, and oxygen is 187. So the pressure of helium then looks like it happens to be, do the math, 219. And that would be the answer to the first question. Now, I have a pressure, I have a liters, and I have a temperature. I want to know the mass. PV equals nRT. I can solve for N here, for helium. So N equals PV over RT. The problem I have is the pressure is 219. So 219 millimeters of mercury. We know that there are 760 millimeters of mercury in 1 atmosphere. That gives me 0.290 atmospheres. Now we can solve. N equals pressure was 0.290 atmospheres, and that's important. It has to be in atmospheres. The volume is 12 liters from the problem. R is R, 0.08206 liters, atmospheres, moles, Kelvin. And the temperature was 273. So the number of moles of helium is 0.155 moles of helium. It wants the mass. Okay? So we'll take our 0.155 moles of helium. We know 1 mole of helium is 4.00 grams of helium. And so that will give us 0.621 grams of helium. And that's where we usually stop. So with that, that'll conclude the video. Let me know if you have questions. Take care, guys. We'll see you next time.